Continuing on here at the Pixel Farm stand, my name is Daryl Shale and I'm the Visual Effects Product Manager at the Pixel Farm. And in this session we're going to take a look at PFDepth, which is our new application for total scene reconstruction, depth map creation, and 2D to 3D conversion that we released right here at IBC 2012. Now before we get too deep into it, I just want to explain the difference between PFDepth and how most facilities are currently doing stereo conversion work. Typically what gets done is a lot of rotoscoping. You might be using Mocha or Silhouette to create a bunch of detailed rotoshapes that represent objects in the scene, export those out to a 3D compositor like Nuke or Flame, and then you apply an arbitrary gray value to that shape. The darker it is, the further back in the scene it will be, the brighter it is, the more forward. The problem with that is that there's no real relationship between that value and the actual world space of the scene, let alone the camera's position. And this is how PFDepth is fundamentally different. Everything in PFDepth is based on a real-world environment, real-world cameras that exist in it, and actual camera-to-object distance values frame to frame. The result's a dimensionalized scene that's much closer to the perceived shape and depth of the actual environment where it was shot. Now, that's not to suggest that you can avoid roto altogether, and if you're using Mocha or Silhouette, we'll support that roto directly in PFDepth. But if you're not, we've got some really cool tools in PFDepth that can speed up that entire process a ton, so bear with me. So before I go any further, I want to talk a little bit about how PFDepth uses depth maps, which is pretty fundamental to the workflow. So here I have a scene which is obviously all CG, but if I have a depth pass for this, I can use that to create my stereo view. And this shot really does allow me to demonstrate how the depth maps are utilized. So here I have my clip input node, and the clip input node allows me to assign parameters defining the actual shot. Things like the in and the out points, the frame rate, focal length, film back if that information is all known. But more importantly for stereoscopic conversion, what the near plane and the far plane is. Now obviously this scene is a lot further back than 10 feet. But I'm going to leave it at the default so that it allows me to display some errors downstream. Now I'm working in feet here. The unit of measure or the scene scale is defined by the parameters. So if I go to the Generals tab, we can see scene scale or scene units. We can choose miles, kilometers, meters, feet, inches, centimeters, and millimeters. Now I'm going to continue working in feet. And what I want to do is utilize an existing depth map. So here it is. I can play that back and we can see it. And I can bring that into this scene literally by dragging and dropping it from my bins into this area here, which is ZDepth import. So after I do that and I take a look at this in 3D view, we can see how the image is currently being worked with. We've got our camera frustum, we've got our field of view, and we've got our plate. Now there's no depth associated with this yet, even though we've imported it, because what we have to do is normalize that channel and also make it linear. It's all depending on how it was exported out of the 3D package. But after I turn on those two parameters, we can see that we now have the depth for that scene. And if I turn down my transparency, you can see that we now have the depth map. So now that we've got that, what we can do is set up a camera rig to literally shoot all of this geometry. So we're going to do that using the stereo render node, and by turning that on we can see that we have, well, actually a real mess here. The stereo effect is being way overemphasized, and the reason being is we didn't accurately set our near plane and far plane units. So when we take a look at this, if we had to use it, there's a couple of things that we can do. First of all, I've got this area here which is called disparity scale, and the disparity scale parameter is used to apply a scale factor to all pixel disparities during rendering, so essentially increasing or decreasing the stereo effect. And similarly, we've got the disparity offset, which can be used to change the perceived position of the entire scene either forward or backward relative to the position of the screen. So how much is going to be protruding from the front of the screen and how much is going to be pushed back. So for the disparity scale, first of all I'm going to turn on this area here which is called comfort zone violations. This is based on some basic viewing conditions that we've set up, and everything in PFDepth is based on the human condition. So if I turn this on, it's based on a simple red, green, and yellow stoplight kind of warning system, where anything that's sort of red is in danger of causing comfort zone violations in the form of things like eye strain and motion sickness, and as we progress back into green, everything becomes a little bit more safe. So what I can do is use this to give me a lot of valuable feedback before I've even rendered out the image to tell me if there are going to be any potential problems. So using my disparity scale, I can just change that to a value of say 0.1, and now everything is within safe region. Now looking here at our disparity scale, the 0 point is what's represented as the screen, Everything above it is what's coming out of the scene, or out of the screen, and everything below it is what's being pushed back. So we can now take a look at this again as an anaglyph. I can also look at this as a left eye view and as a right eye view, and all of those can be exported independently. And again, we can take a look at this as an anaglyph. Now, the real way that you would want to do this is by going up and setting actual known values for this. If they are known, otherwise you're going to estimate it, which is also fine. But in this case, we're going to say that the near plane is approximately 5 feet away from the camera, and the far plane is approximately 100 feet away from the camera. So now again, we can import the depth information and create our stereo render node. And now when I turn on the comfort zone violations, everything is well within range. Now, the next thing that I would want to make adjustments to, if I was working on this for real, is the convergence. So if I take a look at this in the 3D view, we can see where our convergence is. It's way back here in the scene. So in this shot, perhaps we want the convergence to be on this building. So the way that I can do this is if I zoom in, we can see the building right here. I can either drag right in this window and make changes. I could click on the calculator and say I want this to be 30 feet away from camera, and you can see the change. Or what I like to do is by holding down the command key here on my Mac and literally dragging this forward, I can position that absolutely where I want it to be. So again, I'll just move it a little bit further back. And now our eye is converging right on top of this building. So I'll just go in full screen in the cinema and blow this up a little bit and play this back, and we can see the result. So you can see here we've got a tremendous amount of depth and control, even with a scene that's already been pre-built for us. We already have the depth map. We haven't had to create anything, but we still have a tremendous amount of control over how this scene is being perceived in stereo when being rendered out. Okay, so here's a shot that we're going to work on, and as we can see here when we play this back, we've got our boy and he's walking across our bridge. So what I'm going to do is give you an example of how we can use rotoshapes to segment individual depth layers in 3D space to do a 2D to 3D conversion on this scene. So looking here at the clip in node, we can see here we've got our focal length assigned. I assigned it to 40 millimeters. We've got the near plane and the far plane assigned to 6 feet and 50 feet respectively. And I've also assigned a film back preset, a camera preset for the Canon 7D, which is the camera that I use to shoot this. Now, the next thing we would use is the Z-Depth object node, and if I click on that, you can see the Z-Depth object node is where we do all of our rotoscoping, and this is based on a parent-child relationship. You can see here, for example, I've got the boy's head. If I collapse that, they disappear, and by expanding them out, I can see I've got his head, torso, right arm, right leg, and left leg. And that's all of these individual layers that come together to build the boy, and of course we've got all of these other layers back here. So I'll show you how we went and created those. What I'm going to do is go to my list of nodes, and I'm going to select Z-Depth object, and I'm going to take the output from the Orient Scene node and place it into there. And the next thing I'm going to do is start creating some layers. So let's create a layer, and we'll call this boy. And you can see here I've got a number of different parameters. The edge type, I could use hard edge, soft edge. What I'm going to do is leave it on adaptive, and you're going to see why in a second. I can also set the edge width. I can set the edge smoothness, and I can draw an X, which means draw an X-spline, or I can draw B, which is draw a Bezier. Now, if you're using Imagineer's Mocha, or you're using Silhouette Roto to do all of your rotoscoping, we can directly support the splines exported from those two applications. But if you didn't have them, and you didn't want to draw an X-spline or a Bezier, what I like to do is use my Paint Boundary tool. So if I zoom in on the boy's head, for example, I can select that, and you can see I've got a brush with a crosshair. And I'm just going to trace really quickly around the edge of the boy's head and close that off. And you can see when I hit the escape key, I've now got an inner shape and an outer shape for this X-spline. I didn't do any real detailed rotoscoping, I just did a really quick shape. What's cool about this is if I turn on show color, because I've got my adaptive mode set, you can see that it's actually done all of the detailed rotoscoping for us as identified by this arbitrary color that's been assigned for that layer. And this is what's really cool about PFDepth, is that if you have to do rotoscoping, it's kind of like the biggest necessary evil for when you're working on 2D conversion work. But if you do have to rotoscope, we've got some tools in here that allow you to speed that process up significantly. So all I did was draw a really rough shape, and it's automatically separating the foreground from the background. I can also go in and start adjusting things such as the edge fall off, for example. You can see how it's affecting that layer. So if I wanted to make it a little bit of a harder edge, I could expand that out just a little bit. And what I can do now as well is switch over to my tracking tab. And once there, I can turn on a number of these different parameters such as scale, perspective, illumination, robust tracking, depth tracking, all that kind of stuff. I can also use incremental tracking, which is going to sort of reset itself on a frame-by-frame basis. But if I got this basic mask shape set, I can now start tracking that forward. And what's happening is that it's using PFDepth's own planar tracker to track that shape across the rest of the sequence. So you can see it's reanalyzing itself on a frame-by-frame basis and continuing to identify all of those foreground and background layers. So if we were to take a look at this now in 3D space, we're looking at this as in a proxy mode here. We can see we've now got the boy's head floating out in space. I could turn on the ground plane if I wanted to. I could turn on my horizon, all that other stuff. But we've now segmented the layer for the boy's head. And we want to do that for all of the layers in the scene that we want separated in Z-space. So these are essentially all already done, but I'm going to show you how we can take it one step further. We can sort of drag through here and you can see what's going on. I can also randomize the shapes randomize the colors just to make things a little bit easier to see. It doesn't actually change anything, it's all just for display purposes. But there's all of the layers for the boy. We've got the ground, we've got the wall here, we've got the chains, we've got these pillars. But now if I take a look at this, I'm just going to turn off the show color. And if we take a look at this in 3D space, you can see that we've got some really interesting stuff going on here. And what's most important is that all of these shapes have some actual geometry assigned to them. I'm going to show you how that comes together. First of all, for all of these individual layers, what we do is we assign a depth assignment. And this is something that's significant about the way PFDepth works. Everything in PFDepth is based on a real-world camera to object distance value. We're working with real world environments, we're working with real world camera models, and what's cool about this is that if I assign a value such as 14 feet to an object, I'm telling PFDepth that that object is 14 feet away from the camera as defined by, as we talked about earlier, the scene units that we've defined in our preferences. So because we know how deep the scene is, we know what film back we're using, we know what the focal length is, all that kind of stuff, I can assign a very specific value to this. So if you were to take a look at the depth map for this, as opposed to bringing these layers into a 3D compositor and assigning an arbitrary grayscale value to this, the brighter it is, the closer it is, the darker it is, the further away, this value of gray is representing specifically 14 feet, well, 14 and a half feet away from camera. So the values are very, very specific and based on the world space. Now, the other thing that we've got going on here, if we zoom in here and take a look at this, our boy has actually some real 3D shape to him. And there's a few different ways that we can create that kind of stuff. What I'm going to do is switch over to my modifiers tab. And right now we've got the boy's head selected. And you can see here that I've used a radial modifier. So what the radial modifier does is, if I turn on modify, you can see here that we've got basically a circular area that represents the area that we're using for the boy's head. So if I make adjustments to this, for example, if I start to make adjustments to the size of that radial area, you can see what's happening here in the 3D view. Likewise, with things like the scale of that, you can see what's happening. It's actually changing the relative proportion of the shape that we've assigned to that layer. So we've got this kind of nice rounded shape, and again, it's not geometrically correct, but what it does is it gives us a real surface to shoot against. So it's going to help us in two things. One, it's going to give the illusion that there is some actual dimensionality to what is otherwise a postcard in space. And the other thing is it's going to help with things like inpainting, because what we have is a curved surface now. So when we bring this into our stereo render node to create our second camera view, there's actually a surface now that the second eye camera is shooting across. The problem with postcards in space is that if the camera's offset, you're actually shooting into a gap, and that's why you have to do inpainting. With this technique in PFDepth, it eliminates almost entirely the need to do any sort of inpainting. And we do some pretty clever internal processing to assist with the inpainting as well within the stereo render node. So there's the boy's head. And as I mentioned, all of the other layers are offsets from the head. So the boy's head I've set to a value of 14 feet essentially. His torso is set to a value of minus 0.3 feet. So his torso is sticking out a little bit further from his head. So what this means is I can make changes to the position of the area that I've identified as his torso, but if I select his head and I move it, you can see all of the other layers are moving along with it. So the reason this is significant is if I had a scene where, for example, the actor is walking toward the camera, I don't want to necessarily figure out the distance offset for each one of these segmented layers. What I want is the distance for the central object, and then just create basic animated offsets for the areas that I need to do that for. Now, other things, I've got the ground, for example. So the modifier that I use for the ground is the ramp modifier. So you can see that it's essentially extruded out towards the camera. And if I make changes to the thickness of this, you can see what's happening. The wall is using it's not using a modifier per se. The modifiers that we have is a ramp modifier, radial, rotoshapes, blobs, corner pins, cylinders, and planar perspectives. But what I'm using for that wall is actually the image map modifier. And the image map modifier is using the luminance values of the backplate to essentially create a bump map. It's using the different grayscale values to create an aggregate surface. So again, just something else that isn't necessarily geometrically correct, but it's a nice sort of random rough shape for the camera to shoot across to create something that's actually tricking the eye into thinking that there's actually depth there. Same thing with the pillars. I've got the left pillar, the right pillar, and the chain. So again, these are all parented together. So if I make a change to the parent, it affects the child layers. For the modifier, I used the cylinder modifier. So you can see as I start making changes to this, how it's affecting that pillar. It's just basically curving it around its center. And likewise, if I move that center, you can see how it's affecting things. But it's, again, just creating some surface. Now, for the chain, what I did is used a clever little tool in here called the detail keyer. So I'm just going to turn that off. And if we turn on the show color, you can see the chain. There's none of these holes poked out between the chain links. But what the detail keyer allows me to do is sample the background and use that luminance and chrominance information to find the pixels in an area for that layer and effectively knock them out. So I'm just going to turn this on an angle so you can see what happens when I activate the detail keyer. So I turn it on, and you can see now that all of those holes have been punched in there for us. And we can make whatever adjustments we need to the threshold and the smoothness and the erode and the dilate and all that kind of stuff. But again, as opposed to having to go through and roto in between each one of these individual little chain links, it's doing all of that hard work for us. So that's essentially how we built up all of these individual layers. We're rotoing the shape, then assigning a depth value for each layer, then using a number of depth modifiers, whether it's the image map modifiers, the actual selectable pull-down modifiers, or things like the detail keyer to knock out that additional information and create some real shape geometry for each one of these layers. Now you can see here that we're not seeing the entire depth map. What we're doing is seeing the individual layers, and that's defined by the depth cut. If I wanted to bring this up to, say, 100%, you can then see the entire depth map that we're using. But to keep it simple, I usually like to keep it around 10 or 20%, just so that it allows me to much easier. It allows me to see each individual layer a lot more easily. So the next thing we would do is we would bring this all down into our stereo render node. So I've got it piped into here, and assignments that I've set for this, the interocular separation is set to 0.065. I've got my near plane, I've got my far plane, I've got the convergence set essentially at 14 feet. So if we take a look at this, it's converging essentially on the boy. If I wanted to make adjustments to the convergence, again, I could do that by holding down the command key on my Mac and literally just dragging the convergence until it was in a position that I wanted it to be. And I've made some adjustments to the disparity scale and disparity offset. I just want to enhance things a little bit. I've knocked down the scale a little bit because I thought it was maybe a little bit, the stereo effect was a little bit too much. And then I've moved the disparity offset a little bit, of increasing that, and having the ground plane stick out of the front of the camera a little bit more. So, or out of the front of the screen a little bit more. So we can take a look at the rendered result of this, and using anaglyph glasses, you can see the final result. Okay, so here's another scene that we're going to work on. Now, taking a look at this, you can tell that it would typically be a pretty difficult shot to convert. Reason being is that there's a ton of organic material here with all of these vines and leaves and stuff. A ton of occlusion, a ton of really interesting sort of random organic shapes. So this would, typically be a pretty difficult example to work with. But I'm going to give you an example of how we can use depth maps created in PFDepth to do a conversion on this pretty much completely automatically. And what we're going to do is use some interesting information that we can export from PFTrack, which is another application from the Pixel Farm used for 3D camera match moving and object tracking, to hint information to the scene and assist us with the creation of these depth maps. So what we're going to do is switch over to PFTrack, and we've got our scene here. And playing it back, we can see everything that's going on. So what I've done is I've done a auto track on this. So just darkening it up, you can see all the trackers that have been placed. And I've done a camera solution and an orient scene to place the ground plane up on top of this rock surface. And if we take a look at this in 3D space, we can see the point cloud and the camera path. Now, exporting this as an FBX, this allows me to export the camera's motion, the ground plane, and the point cloud. Now what's going to happen here is that PFDepth is going to utilize all of this information to assist with this calculation of building up depth maps. So what's going to do is use all of these points in this point cloud, along with the parallax and the camera's position frame to frame and some optical flow analysis technology, to solve a per pixel position of every pixel in the image relative to the camera's position on that point in time. So to show you how that works, let's go back over to PFDepth. And for the clip input node, I'm going to import an FBX and just navigate to where that lives. So there's the break wall FBX. It's going to ask me what camera do I want to bring in, which take. Do I want to bring in the import? Do I want to bring in the nulls and replace the existing nulls, which I do. So I'm just going to hit OK and let that import. And there's our point cloud, which is a little bit difficult to see, but you can see that now that when I darken the scene up, I can turn on the ground plane if I wish. But looking at this in our perspective view, we can see our total field of view here. What I'm going to do is assign a far plane value of 30 feet for this. It's certainly not 50 feet deep, so we're just going to bring that back a little bit. And but you can see we actually have chrominance and luminance information for that point cloud as well, and that's going to give us a little bit more information when we are trying to calculate a depth map based on these individual depth cues that have been created by tracking the scene in PFTrack. So let's take a look at how this works. What I'm going to do is create a ZDepth solver node, and let's plug into to it. Let's just move this up to the side here. And what I'm going to do is I'm going to switch from frame range over to current frame. I'm just going to park it on, say, frame 40, for example. And I can adjust things like look head values and iterations, but I'm just going to create a really quick depth map here based on this information. So I'm going to say solve. And as it crunches away at this, it's now giving us a depth map. So now when I take a look at this in our perspective view, we can see what's been given to us. First of all, let's switch it over to a point to our point cloud. So as I zoom in here, you can see we actually now have a massive point cloud, and what these points are is quite literally every single pixel in this image extruded in Z-space relative to this camera's position at this point in time. So you can see it's solving all of those rocks, it's solved that twig that's up front, it's given us a really elaborate and detailed organic shape. So now what I can do is I can switch this from a point cloud over to a triangular mesh. And again, when we look at it from the camera's position, we have an extremely elaborate object. I can bring the depth cut up again to about 100%. and it fills in the blanks, and there's our single frame depth map interacting with our backplate to create this piece of geometry. So the next thing we want to do is we want to take that single frame depth map. You can see it flash through because it's only on frame 40. Likewise, when we take a look at here in perspective, we only have it on a single frame. We can take this, and instead of calculating it for every single frame, what I can use is my ZDepth tracker node to take this and track it into the rest of the frames. So I could adjust the spatial weight, which would give tolerance for moving objects. The position weight gives us more emphasis on the camera's position. I'm just going to leave it as defaults. We're going to say auto fill in missing depths, and we're going to start tracking it forward. So what it's doing now is it's taking that initial depth map and building on it. So it's saying, okay, well, I already have all of these depth cues. Let's use those depth cues to hint depth information to the next frame. On the next frame, it's going to look at the camera's position relative to the point cloud and the depth information we just fed it from the previous depth map and fill in the blanks. So as it continues to go through on a frame-by-frame basis, it continues to reevaluate itself and generate additional frames of this depth map as it continues along the timeline. So now if I scroll through, you can see all of the frames that have been created there. Likewise, we can take a look at this from our scrolling through from our camera's position. And I can then plug this into a stereo render node. So we've assigned some basic values. I set the far plane, as I mentioned, to 30 feet, near plane to 1 foot. Interocular separation is 0.065. I've increased the disparity scale and disparity offset. So if I turn on the disparity histogram, we can see here's our 0 point. So I've got pixels coming out of the image, pixels going further back, out of the screen, further back on the screen, and there's our convergence on the foreground. And we've got our final scene. So that in itself is pretty cool. But if I really wanted to take the time and get more elaborate with this, what I could do is go the route of solving a depth map for every single frame. So again, what I'm going to do is create a ZDepth solver node. Here we are. And instead of using it on the current frame, I'm going to switch it over to clip. And we will hit solve. So now as it's doing its calculation, it's adding in an additional layer of analysis. And this is going to get us some very, very, very detailed information. So it's completely reevaluating itself. It is using the hints, but starting from scratch. So it's taking a lot more time to evaluate the position of all of these different objects and create the depth map. So you can see here we've got a lot more detail, particularly in the background, right down to the shape of individual twigs and things. I'm not going to make you sit through this. We can take a look at the one that I've already pre-calculated. So you can see here we've got individual blades of grass, an immense amount of detail in this. But there are a few problems. It didn't get all of the things right. So there's a couple of different things that we can do to fix that. First thing we might do is use a ZDepth merge node. And what that's going to do is take our depth map and start merging frames together. Now, I can look at the outlier area, I can look at the image similarity, I can look at the frame window. So the frame window is saying how many different frames of this depth map upstream and downstream do I want to look at as I'm merging things together. But more importantly, what's going to happen is that it's going to get rid of some of the random chatter that can happen with this. I'm just going to crank this up to 100 again so we can see what's happening with the depth map itself on a frame-by-frame basis. Now, when I say random chatter, I'm talking about these little bumps that kind of get improperly interpolated frame to frame. And the reason that kind of stuff happens is because it's basing its solve on that position in time. So what we want to do is compare multiple frames against each other to get rid of that randomness, because the stuff that's static, or the stuff that's most consistent, should be there, and the stuff that's incredibly random shouldn't. So what I'm going to do is just hit merge. And as that happens, you can see we've got much more consistency as it's merging those frames together. We're getting rid of virtually all of that chatter. We're introducing a lot more detail, particularly with those individual blades of grass and reeds and twigs and all that kind of stuff in there. And it's creating an extremely detailed depth map. So I'm just going to stop that again, and we can take a look at the version that I've already created, or that I've already merged. And going through, we can see that it's fixed the vast majority of everything, but there's a few areas that it still needs a little bit of help. So for that, we're going to use our ZDepth Edit node. So the ZDepth Edit node is a full depth painting system. So if I had to start painting from scratch, I can. I can use brushes, I can paint strokes, push data forward or backward, I can pull it forward, I can clone depth information, I can create gradients. So, and I'll give you an example of that a little bit later. I can smooth areas, erode them, dilate them, create edges, erase things, fill things, and denoise them. What I'm going to do is I'm going to use the erase brush, because I want to show you how we can work on this without having to get involved in like really detailed depth painting. So here we've got a few frames where the edge of frame didn't solve particularly well. So what I'm going to do is literally just erase those pixels. And if we take a look at this in perspective, you'll be able to see a lot better what's happening with those. You can see we've got these pixels here that have been extruded completely incorrectly. So I can literally just paint those out and remove them. And what's happening is we're actually poking holes in the depth map. So I can go through and continue to see if there's anything more. There's some stuff up here that we want to get rid of. And we want to do that throughout the entire sequence. So that's what I've done in this version of the depth edit node. So we've got our holes poked, and now what I want to do is fill in the blanks. There's another little problem right there. There's some stuff right there. So anyway, I'm just going through and erasing things that I think might be problems. Now what I'm going to do is switch from the ZDepth Edit node, the paint area, over to the fill area of the ZDepth Edit node. And I'm going to switch from current frame over to the entire clip. And I'm going to say autofill. And what it's doing is automatically filling in all of the blanks or all the holes that I punched using my paint tool when I erased all those pixels. So now when I go to those first frames where I punched those holes in, it not only filled them in, it actually filled them in with data based on pixel information from around the pixels that I just filled in the blanks. So again, we can play this back, and if there is an area that was still causing us a bit of a problem, we see it right there on that frame. Might that be? It's right here. There's a couple of little black spots. I could also, if I didn't get those before, what I could do is switch back over to the erase tool, poke a hole there, poke a hole there. I can also switch now over to my fill brush and fill it in with a paint stroke and fix it that way. So multiple different ways that we can go through and start editing individual depth maps. And then of course we're putting it into our stereo render node to create the final stereo effect. And I'm going to let you look at the pre-rendered version of this so we don't have to cache all of that information, but we'll take a look at this now as an anaglyph and play that one back. So here's another shot that we're going to work on, and it's kind of an interesting shot because of the scope of depth and just how deep this scene actually is. I'm going to show you a couple of different ways that you could possibly attack this shot. Now, as we did in the previous example, I've used some information exported from PFTrack. So if I jump into PFTrack, we can take a look at what we've done to solve this scene. Here's the auto track node. So I've gone through and done a camera solution, and we can take a look at the 3D solution for that here. We've got our camera motion and our point cloud. But what I wanted, because of the immense depth of this scene, what I really wanted was a really dense point cloud. So what I've done is, after I've got my initial camera solution, I've retracked in a whole bunch of additional trackers and then solved those into the scene. So now I have a much denser point cloud. I've oriented the scene. I've made some basic adjustments to this just to smooth out the curve, and now we have our dense point cloud along with our camera motion. Now the other thing that I did is in PFDepth, or in PFTrack, we actually can do ZDepth solving, and we've been able to do this for quite some time. So in this case, what I wanted to do is give you an example of how you can use depth maps that have been created in PFTrack. Now we've already shown you how you can bring in a depth map that was exported out of CG, but if you have a depth map that's been created in a compositing or a tracking application, we can bring that in via OpenEXR. So here I have the ZDepth solver, and it's very rough to start with, but that's okay. We want to use it essentially as a starting point. So now what I want to do with this is export it, and I'm going to export it as an OpenEXR RGBA plus Z image. So now when I go back into PFDepth, what I want to do first of all is import the FBX for the camera motion and for the dense point cloud. So I'll bring all of that stuff in. And after we've rendered out the depth map, I can bring that OpenEXR sequence into my bins and grab it. So there's our point cloud. I can go to my bins now and grab that OpenEXR image and drag that right in here, which says ZDepth import. Now when I bring it in and we take a look at this in 3D space, we can see that it's flat. So what I want to do is actually normalize the channels because I exported it normalized. And now we have our initial extruded depth map information. Now what I can do with this is, again, go back to my list of nodes and bring in a ZDepth merge node. So I'm going to take this directly out of the clip input node, put it directly into the ZDepth merge node, and start merging it. So now what it's going to do is take a look at all of this random information and start smoothing it out. And we can use any number of frames upstream and downstream for comparison. In the real version, of course, as you can see here, I used 10 frames of analysis, which takes a little bit longer because you're analyzing more frames, but you can see the results are a little bit more solid. And then what I did is I wanted to address some of the larger volume of chatter that we had going on in here. So I went into a ZDepth edit node and essentially started poking holes in areas that were giving me some concern. So down here and up here, I showed you this example a little bit earlier, but literally just painting out using the erase brush all of those areas. I then went into I added another ZDepth edit node just for the sake of demonstration. I could certainly flip over to the fill tab, but I wanted to work non-destructively. So I added another ZDepth edit node and then went into the fill tab and then selected autofill for the entire clip range. And that's gone through and started sorting a lot of that stuff out. I then added another ZDepth merge node to get rid of some of the sort of high intensity difference between frames. And then that has given us the result that we see right here. So again, we're looking at this now as the rendered out anaglyph version of the final shot. Now I'm going to show you another way that you can go about attacking this, and this is using only the ZDepth edit node. So what I'm going to do is create a new ZDepth edit node. So right now we are looking at the depth map that's being provided from PFTrack. If I want to get rid of that and start fresh, I can go up into my clip input node and say remove ZDepth. So now when I took a look at my ZDepth edit node, I no longer have any depth information. So what we're going to do now is we're going to start from scratch. So what I can do now is select a paintbrush, and what I want to do is assign a depth value to that paintbrush. So for the surface of this building, I'm estimating this is maybe 350 to 400 feet away from the camera. So let's split the difference, and we're going to give it a value of 375 feet. I can then go through and start painting in my depth information. And the stroke that I'm painting right now represents 375 feet as I've assigned for this brush. So it's not an arbitrary, gray value that I'm just going to sort of lighten and darken and try and get it right. This value of gray specifically represents 375 feet relative to the rest of our scene scale. So there's our initial stroke, or the paint stroke that we painted in for the top of that building. Now for some of the other buildings, maybe this surface here is approximately 650 feet. So we can type in that and paint in a quick stroke for 650. Maybe this one over here is 730, maybe 720. So we'll paint that in. So you can see as I assign a different value of distance, the level of gray is completely different and representing that depth value. So And all I'm really painting in right now is depth cues. Again, let's paint a few more in. Maybe this one here is, let's say, maybe 750. So we can say 750. And we'll paint that in. And maybe the ground is, say, 870, because we're saying that that is how far away from the camera the far plane is. And by the way, these values were automatically imported along with the depth information that we exported out of PFTrack. So I haven't assigned this, it came in as part of that OpenEXR. So if the ground is 870 feet away, we're going to say 870, and then start painting in the ground. And as you can see here, I'm really not getting detailed with my painting. I'm just literally painting in cues. I can shrink my brush down a bit. Maybe paint in this alleyway here. And you can see now how that's all starting to come together. So what I want to do is paint in cues for, get on the right frame here. So there's all the paint information, or all the depth information that I've painted in for frame 95. And I can rotate around and see the result. So now what I can do is, let me just get rid of these two nodes that we were working on earlier, and I'm going to make a copy of this because we want to work non-destructively. And what I want to do now is switch over to my fill tab, and for the current fill, or for the current frame, I want to say autofill. So it's going to take a look at the parallax that we have and those initial depth cues, and then fill in all of the blanks to give us our depth map. So now this depth map is only relevant to one single frame. But now what I can do is switch over to my track tab. I'm going to increase my position weight because this is based on the camera's motion as opposed to an object motion. If we were basing our movement on an object motion, I would increase the spatial weight, but in this case I'm going to increase the position weight. And I can start tracking this initial depth map into additional frames of this footage. And if there are some areas that I get wrong, I could always then add a ZDepth edit node to paint in that specific information. But the point here is to say, we can create very elaborate depth maps and per frame depth maps very, very quickly just by feeding PFDepth some useful information. In this case, we're feeding it some depth cues in the form of a point cloud, and then we're also painting in some strokes to identify, in this case, planar surfaces and assigning a depth value to them, and using those as a hint to automatically solve the rest of the depth map and fill in all of the blanks. So here's our last example in this introduction to PFDepth. Now, I'm going to show you some stuff that's pretty cool here. What I have here is a shot, and you can see we've got, motion capture dots. I've traditionally used this as a demonstration for showing you how to do motion capture in PFTrack, as well as geometry tracking. And what we're actually going to do in this is use geometry tracking from PFTrack to provide some additional very cool and very unique information to PFDepth when we try and do a 3D conversion on this scene. So let's jump into PFTrack then, and we can see we've got our scene here. So what I've done to set this up is I brought in an edit camera node, and an edit camera node literally just puts a 3D camera and puts it into our environment based on the values for X, Y, and Z translation and rotation that I've set up. And then I've brought in a geometry tracking node. And the geometry tracking node is truly unique. I get into a lot of depth with the geometry tracking node in the PFTrack demo that I'll be doing later on here today. So please join us for that. But in this scenario, what we're doing is we're essentially using geometry to do a track of this facial capture and then export that geometry, which is going to be converted into a depth map automatically within PFDepth. So what is geometry tracking? Well, in this case, we're actually using the vertices of this triangular mesh to do the track as opposed to points doing the track. The reason this is particularly effective on things like performance capture is that with object tracking, and in this case we are tracking an object, if you're using point trackers, they all have to be static relative to each other. But in this case, you can see the points are anything but static. His lips are moving, his forehead is compressing, his cheeks are puffing. So point trackers simply will not solve this object. But what we can do is use a geometry tracking node to use the vertices of this geometry to track. Moreover, we can actually use what we call deformable groups to track each one of those individual regions on his face. So again, I get into more depth on how to build this up in the PFDepth or the PFTrack demo later today, but what I've set here is deformable groups for his bottom lip, his brow, his cheeks, his jaw, and his top lip. And for each one of those regions, I've assigned how I want it to deform. So, for example, his cheeks are going to translate on X and Y, rotate on X, and scale on X and Y. So those areas are now going to become elasticized, and as it tracks, it's tracking each one of those regions and allowing them to puff and compress and expand along with the features of his face. So if we take a look at this in 3D space and we play it back, we can see that our geometry is now deforming. Now, as we can see, the geometry has a very specific offset in 3D space relative to the camera's position, and the geometry itself has a specific depth thickness. So what I can do with this is now automatically convert this into a depth map in PFTrack or in PFDepth by exporting from PFTrack as an FBX. So if we go back into PFDepth, I'm going to import an FBX. I'm going to point to that facial track FBX that we've exported and bring that in. And we can see here now that we have the geometry along with the camera. So what I'm going to do to set this scene up is I'm going to set the far plane up to be, let's say, I don't know, let's say 15 feet. And what we want to do is create the rest of the depth map for the rest of the scene. And we're going to do that using our ZDepth edit node, which is our depth painting system. So if I connect into that, we can see we have the depth map for his face. And we can see there it is in 3D space away from the camera. And what I'm going to do is assign a paint stroke, and I want the background to maybe let's say 12 feet away from camera. So if I assign a stroke of 12 feet and start painting that in, the depth value that I'm now painting represents 12 feet. So I'm just going to really quickly start to fill this in. And let's significantly increase the size of our brush just so we can get all that filled in. And let's do some other stuff here. For example, maybe the top of his head here is about 7 feet away from camera, so we'll assign a stroke of 7. And I'm going to just paint in the top area of his head. Maybe his earlobe is, say, 7.3 because it's sitting a little bit further in front of the back of his head. So we'll just do that. And maybe his crook of his neck is maybe 8 feet. And we'll say 8 feet for his shoulders as well. So I'll put a stroke in for that. So you can see I'm just providing depth cues. I'm not doing any detailed painting. Let's say let's increase the size of our brush. Let's say the back window frame here is 10 feet. And then of course we have, let's just get rid of that by selecting our erase brush. And of course we have this area over here that I forgot to paint in, so what I can do is sample that same area, which gives me 12 feet, and then I can paint a stroke in for that area there as well. And if I went over like I did here, I can just erase. And again, we'll sample this and paint that back in. Okay, so I've got my my initial depth cues painted in. So the next thing that I can do now is I can switch over to my fill tab, and for the current frame I can say autofill. And it's now going to take a look at the depth cues that I've set up and automatically fill in the blanks. So now when I take a look at the shot, we can see we now have a full depth map. We've got his shoulders in the scene, we've got the rest of his face, we've got the window frame, we've got the back window and the side over here. And then I can switch over to the track tab and start tracking this initial depth map into the rest of the frames. After I've done that, what I can do is I want the facial depth map to be based solely on the geometry. So what I can do is use a Z-depth composite node, and the Z-depth composite node is going to allow me to combine depth maps together. So first of all, I have the depth map that I've painted and tracked, and then I have the depth map that came in the form of a piece of geometry. So now I can combine those two together. We have in this version of it, we've got a slightly different assignment for the background, but that's fine. You get the idea of what's going on here. We've got all of this version of the depth map. Then what I did is I used a Z-depth edit node to just sort of paint out a couple of errors that were occurring, and then merge them together, and then used a couple of Z-depth filter nodes to refine things a little bit. First of all, the median filter is going to smooth the edges a little bit, and then the bilateral filter is going to reintroduce some of the detail and maintain the sharpness of those edges. So you can see here we've got an incredibly detailed depth map. By combining a couple of different techniques together. In this case, we are solving the actor's face based on a piece of geometry, and then painting in depth cues for the rest of the areas of the background, and then literally just using a fill command to fill in the blanks. And we can take a look at the final version of this and play this back as an anaglyph. So that's all I have for you for this initial introduction into PFDepth that we just released right here at IBC this past Friday. If you have any questions about PFDepth or any of the other Pixel Farm products, please don't hesitate to come and speak to me or any of the other farmers around the Pixel Farm stand. Otherwise, thanks very much for your attention, and enjoy the rest of your day right here at IBC 2012.